In philosophy, the philosophy of physics studies the fundamental philosophical questions underlying modern physics, the study of matter and energy and how they interact. The philosophy of physics begins by reflecting on the basic metaphysical and epistemological questions posed by physics, causality, determinism, and the nature of physical law. It then turns to questions raised by important topics in contemporary physics: physical cosmology, space, time, and the origin and ultimate fate of the universe, thermodynamics and statistical mechanics, energy, work, randomness, information, quantum mechanics, the rival interpretations thereof, and its counterintuitive conclusions. Centuries ago, the study of causality, and of the fundamental nature of space, time, matter, and the universe were part of metaphysics. Today the philosophy of physics is essentially a part of the philosophy of science. Physicists utilize the scientific method to delineate the universals and constants governing physical phenomena, and the philosophy of physics reflects on the results of this empirical research. Purpose of physics. According to Niels Bohr, the purpose of physics is not to disclose the real essence of phenomena but only to track down relations between the manifold aspects of experience. Many, particularly realists, find this minimal formulation an inadequate formulation of the purpose of physics, which they view as providing, in addition, a deeper world picture. Philosophy of space and time. The existence and nature of space and time are central topics in the philosophy of physics. Time is considered to be a fundamental quantity, because at present nothing is more basic than time. Thus time is defined by a measurement, by its standard time interval. Currently, the standard time interval is defined as 9,192,631,770 oscillations of a hyperfine transition in the 133 cesium atom. What time is and how it works follows from the above definition. Time then can be combined mathematically with the fundamental quantities of space and mass to define concepts such as velocity, momentum, energy, and fields. Both Newton and Galileo, as well as most people up until the 20th century, thought that time was the same for everyone everywhere. Our modern conception of time is based on Einstein's theory of relativity and Minkowski's space-time, in which rates of time run differently in different inertial frames of reference, and space and time are merged into space-time. Time may be quantized, with the theoretical smallest time being on the order of the Planck time. Einstein's general relativity as well as the redshift of the light from receding distant galaxies indicate that the entire universe and possibly space-time itself began about 13.8 billion years ago in the Big Bang. Whether and how the universe will ever end are open questions. Time travel. Some theories, most notably special and general relativity, suggest that suitable geometries of spacetime, or certain types of motion in space, may allow time travel into the past and future. Concepts that aid such understanding include the closed time-like curve. Albert Einstein's special theory of relativity predicts time dilation that could be interpreted as time travel. The theory states that, relative to a stationary observer, time appears to pass more slowly for faster-moving bodies. For example, a moving clock will appear to run slow. As the clock approaches the speed of light, its hands will appear to nearly stop moving. The effects of this sort of time dilation are discussed further in the popular twin paradox. These results are experimentally observable and affect the operation of GPS satellites and other high-tech systems used in daily life. A second, similar type of time travel is permitted by general relativity. In this type, a distant observer sees time passing more slowly for a clock at the bottom of a deep gravity well, and a clock lowered into a deep gravity well and pulled back up will indicate that less time has passed compared to a stationary clock that stayed with the distant observer. These effects are to some degree similar to hibernation, or cooling of live objects almost indefinitely suspending their life, thus resulting in time travel toward the future, but never backward. They do not violate causality. This is not typical of the time travel featured in science fiction, and there is little doubt surrounding its existence. Time travel will hereafter refer to travel with some degree of freedom into the past or future of proper time. Many in the scientific community believe that time travel is highly unlikely, because it violates causality, i.e., the logic of cause and effect. For example, what happens if you attempt to go back in time and kill yourself at an earlier stage in your life? Stephen Hawking once suggested that the absence of tourists from the future constitutes a strong argument against the existence of time travel, a variant of the Fermi Paradox, with time travelers instead of alien visitors. Hitherto there is no experimental evidence of time travel, making it a mere hypothesis as opposed to an empirical fact. Space is one of the few fundamental quantities in physics, meaning that it cannot be defined via other quantities because there is nothing more fundamental known at present. Thus, similar to the definition of other fundamental quantities, space is defined by a measurement. Currently, the standard space interval, called a standard meter or simply meter, is defined as the distance traveled by light in a vacuum during a time interval of 1,299,792,458 of a second. In classical physics, space is a three-dimensional Euclidean space where any position can be described using three coordinates. Special and general relativity use spacetime rather than space. Spacetime is modeled as a four-dimensional space free will. Then we must accept that the world is not entirely governed by natural law. Some have argued that if the world is not entirely governed by natural law, then the task of science is rendered impossible. However, the development of quantum mechanics gave thinkers alternatives to these strictly bound possibilities, proposing a model for a universe that follows general rules but never had a predetermined future. Indeterminism against the proponents of determinism like Einstein and Max Planck. Indeterminism, championed by the English astronomer Sir Arthur Eddington, says that a physical object has an ontologically undetermined component that is not due to the epistemological limitations of physicist understanding. The uncertainty principle, then, would not necessarily be due to hidden variables but to an indeterminism in nature itself. Heisenberg, de Broglie, Dirac, Bohr, Jeans, Weyl, Compton, Thomson, Schrödinger, Jordan, Millikan, Lemaitre, Reichenbach, al. were all supporters of indeterminism. Uncertainty principle. The uncertainty principle is a mathematical relation asserting an upper limit to the accuracy of the simultaneous measurement of any pair of conjugate variables, e.g., position and momentum. In the formalism of operator notation, this limit is the evaluation of the commutator of the variable's corresponding operators. The uncertainty principle arose as an answer to the question, how does one measure the location of an electron around a nucleus if an electron is a wave? When quantum mechanics was developed, it was seen to be a relation between the classical and quantum descriptions of a system using wave mechanics. In March 1926, working in Niels Bohr's institute, Werner Heisenberg formulated the principle of uncertainty, thereby laying the foundation of what became known as the Copenhagen interpretation of quantum mechanics. Heisenberg had been studying the papers of Paul Dirac and Pascual Jordan. He discovered a problem with measurement of basic variables in the equations. His analysis showed that uncertainties, or imprecisions, always turned up if one tried to measure the position and the momentum of a particle at the same time. Heisenberg concluded that these uncertainties or imprecisions in the measurements were not the fault of the experimenter, but fundamental in nature and are inherent mathematical properties of operators in quantum mechanics arising from definitions of these operators. The term Copenhagen interpretation of quantum mechanics was often used interchangeably with and as a synonym for Heisenberg's uncertainty principle, by detractors who believed in determinism and saw the common features of the Bohr-Heisenberg theories as a threat. Within the Copenhagen interpretation of quantum mechanics, the uncertainty principle was taken to mean that on an elementary level, the physical universe does not exist in a deterministic form, but rather as a collection of probabilities, or possible outcomes. For example, the pattern produced by millions of photons passing through a diffraction slit can be calculated using quantum mechanics. But the exact path of each photon cannot be predicted by any known method. The Copenhagen interpretation holds that it cannot be predicted by any method, not even with theoretically infinitely precise measurements. Complementarity. The idea of complementarity is critical in quantum mechanics. It says that light can behave both like a particle and like a wave. When the double-slit experiment was performed, light acted in some cases as a wave, and some cases as a particle. Physicists had no convincing theory to explain this until Bohr and complementarity came along. History of the philosophy of physics. Aristotelian physics. Aristotelian physics viewed the universe as a sphere with a center. Matter, composed of the classical elements, earth, water, air, and fire, sought to go down towards the center of the universe. The center of the earth, or up, away from it. Things in the ether such as the moon, the sun, planets, or stars circled the center of the universe. Movement is defined as change in place, i.e., space. Newtonian physics. The implicit axioms of Aristotelian physics with respect to movement of matter in space were superseded in Newtonian physics by Newton's first law of motion. Every body includes the moon, and an apple, and includes all types of matter, air as well as water, stones, or even a flame. Nothing has a natural or inherent motion. Absolute space being three-dimensional Euclidean space, infinite and without a center. Being at rest means being at the same place in absolute space over time. The topology and affine structure of space must permit movement in a straight line at a uniform velocity. Thus both space and time must have definite, stable dimensions. Leibniz. Gottfried Wilhelm Leibniz (1646–1716) was a contemporary of Newton. He contributed a fair amount to the statics and dynamics emerging around him, often disagreeing with Descartes and Newton. He devised a new theory of motion based on kinetic energy and potential energy, which posited space as relative, whereas Newton was thoroughly convinced that space was absolute. An important example of Leibniz's mature physical thinking is his Specimen Dynamicum of 1695. Until the discovery of subatomic particles and the quantum mechanics governing them, many of Leibniz's speculative ideas about aspects of nature not reducible to statics and dynamics made little sense. For instance, he anticipated Albert Einstein by arguing, against Newton, that space, time and motion are relative, not absolute. As for my own opinion, I have said more than once, that I hold space to be something merely relative, as time is. That I hold it to be an order of coexistences, as time is an order of successions. Quotes from Einstein's work on the importance of the philosophy of physics. Albert Einstein was extremely interested in the philosophical conclusions of his work. He writes, "I fully agree with you about the significance and educational value of methodology as well as history and philosophy of science. So many people today, and even professional scientists, seem to me like somebody who has seen thousands of trees but has never seen a forest." A knowledge of the historic and philosophical background gives that kind of independence from prejudices of his generation from which most scientists are suffering. This independence created by philosophical insight is, in my opinion, the mark of distinction between a mere artisan or specialist and a real seeker after truth. Einstein. Letter to Robert A. Thornton, 7 December 1944. Each 61 to 574. Elsewhere. How does it happen that a properly endowed natural scientist comes to concern himself with epistemology? Is there no more valuable work in his specialty? I hear many of my colleagues saying, and I sense it from many more, that they feel this way. I cannot share this sentiment. Concepts that have proven useful in ordering things easily achieve such an authority over us that we forget their earthly origins and accept them as unalterable givens. Thus they come to be stamped as necessities of thought, a priori givens, etc. The path of scientific advance is often made impassable for a long time through such errors. For that reason, it is by no means an idle game if we become practiced in analyzing the long commonplace concepts and exhibiting, revealing, exposing, those circumstances upon which their justification and usefulness depend, how they have grown up, individually, out of the givens of experience. By this means, their all too great authority will be broken. Einstein, 1916, Memorial Notice für Ernst Mach Physikalische Zeitschrift 17, 10102.